Good day, everyone. My name is Cecil Marie Angel Brother of Group 2, and I will be presenting my design of experiment 8051 base integrated multi-peripheral control system. So starting, here's the EdSim 51DI. So I have the code here already. So next is assemble it and then run. So the main objective is to design a single program that integrates three different peripherals from our previous labs, the keypad as an input, and the LCD and DC motor as outputs. The system will allow a user to control the motor's direction using the keypad with the current status displayed on the LCD. So first, the running the simulation, which is this is the initial state. So we have the update frequency to 100, and then as you can see, this is the initial state. So as you can see, the program immediately initializes the LCD display stop, and the DC motor is stationary as you can see here. This is the system's default safe state. Now, we are going to click or press 1 or hold press 1. Now, now I will test the forward command. When I press and hold 1, the keypad scanning subroutine detects the input. This calls the motor control subroutine, and as you can see, the motor begins spinning clockwise or forward. Simultaneously, the LCD subroutine is called to update the display to forward. You can see here, the rotation is clockwise. Now, we're going to release the 1 key, and now we're going to press and hold the 2 key. So this is the reverse command. By pressing the number 2 key, the main loop detects the new input, calls the reverse logic function, and the motor's direction is reversed to anti-clockwise. The LCD is updated to rev. So you can see here, the rotation is now counterclockwise. Now we're going to release the key 2, and we're going to press and hold key 0. So with pressing the key 0, this triggers the stop command, which sets both motor control pins to 0. Halting the motor, the LCD correctly updates back to stop as you can see here. And this stops. Now, for the next step, we're going to press any invalid keys that are not 0, 1, and 2. So, let's try clicking number 5. So, you'll notice that if I press an invalid key like 5, nothing happens. The program's logic is designed to only act on keys 0, 1, and 2, making it robust against incorrect inputs. So there are two key design features I'd like to point out. First is the I/O port management. I intentionally use the keypad on port 0, the LCD on port 1, and the motor controls on port 3. This design avoids the I/O port conflicts that would occur if we tried to use the LCD, LEDs, and SSDs at the same time. since they all share port 1. Second, the logic is a simple finite state machine with stop, forward, and rev as the states. The wait key release loop is also critical. It acts as a debouncing mechanism to prevent one long key press from being registered hundreds of times. So now we pause or stop the simulation. So this demonstration shows a complete event-driven system where all objectives were met. We successfully integrated three peripherals, managed port assignments, and processed user input to control both mechanical and visual inputs. And that concludes my demonstration. Thank you for your time.